Well, hi there, sports fans, and welcome to another exciting edition of Physics 12. Today we're looking at lesson 2.4, which is what's known as many body problems. Now, what that's referring to is something like this, where you have a few objects that are attached together with strings, and force is being applied to them, and you need to determine, what the acceleration is of each of the different objects and the different masses, and also the tensions in the strings between them. Now, what's helpful in this kind of a situation is that you can deal with the entire system altogether. So if you know what the tension is that's pulling all of the masses, then it's pretty simple to find out what the acceleration is of the system. And once you have that, then you know that that will also be the acceleration of each of the masses, because they are being accelerated all together. So that's how we start. Just again, simply just F equals ma, and the tension on this system of masses is given with T there, and so the acceleration of the system will just be the force that's applied there, the tension force on the system divided by the total mass of the system, and then you can get the acceleration that way. And then what you can do after that is you can divide this into subsystems now, and because we have the acceleration of the whole system, you know that each of the masses is accelerating at that rate, so therefore it's now what we can do is we can find the tension that's pulling these two masses as a subsystem of the entire system. And so that tension there will just simply be these two masses together times the acceleration of the masses or of the system. And then you can find the tension in between the masses as well in that way. So we can look at the whole system together, or we can look at some subsystems as well. And so let's look at an example where we put some numbers in. And so as you can see, I've assigned some masses to the different objects here, and we'll figure out what the acceleration of the system is, as well as the tension of each of those strings in between there as well. And so we'll call that T1 and T2. So we need to find what acceleration of the system is, and T1 and T2. So let's see how we can do that. So once again, we'll look at the whole system together, and then we can determine what the acceleration is of the system. So that's easy enough to do. So we start simply with F equals ma. And so the force on the system now is the tension that's given, it's 36 newtons, times the total of the masses, which is 4.0 plus 2.0 plus 6.0, times the acceleration of the system. And when you do that, you will find that the acceleration of the system, in other words, each of the masses, is 36 divided by 12, or 3 meters per second squared. And so now we have the acceleration of the system, and that will also be the acceleration of each of the masses. And so now we can find the tension in the strings between the masses, in other words, T1 and T2. So if the acceleration for each mass is 3 meters per second squared, then we can look at this subsystem in order to find T1. So T1 then is going to equal the total of these two masses together, 4.0 plus 2.0, times the acceleration of those masses, which is 3 meters per second squared. So T1 then, this tension will be 18 newtons. So we're using a little bit of algebra here in order to do that, but as you can see, it's useful to look at the whole system together and then to break it up into subsystems. And now that we have T1, it's a simple matter as well to find T2, because now we just look at this mass by itself, and so it also is accelerating at 3 meters per second squared. So T2 then has to equal the mass of M1, which is 4.0 kilograms, times its acceleration, and so T2 then will be 12 newtons. So that's how we solve these kinds of problems here. And we'll look at another one, which is a little bit more complicated. Let's see. Yeah, that's just the same one again. An image of the same one. Okay, so let's move on to a somewhat more complex one, like this one here. And you might be looking at this and thinking, oh dear, what do we do now? Well, actually, there's some tricks that I will show you here which will help you deal with a problem such as this. And again, what you're going to start with is what we call the free body diagram. So we will take each of the different objects, each of the different masses, and deal with them separately and draw the forces on each one of them. Alright, so taking this mass by itself, it only has one force on it, which is T2, which is in that string. Then we take this mass. Now this one, yeah, actually what I was going to mention with the previous diagram is that when you have a string between masses like so, this one will experience a force in that direction. This one will also experience an equal force, but in the opposite direction. So in other words, we have a T2 going in this direction on this mass, but we also have a T2 going in this direction on this mass. And that is key then to solving these kinds of problems, is recognizing that again, it goes back to one of Newton's laws, is that for every action there's an equal and opposite reaction. So that means then that if we have a T2 in this direction, we also have to have a T2 in that direction, like so. And then we also have a T1 on this mass over here. We don't know what those are yet, but that's what we're going to find out. Now, here's another trick for something like this. This, obviously, is being affected by the force of gravity, but it's in a different alignment from the rest of them. You might say this is in the y direction and these are in the x direction. Well, guess what? You can just make this one into the x direction, put it in the x direction. As long as you have all of the forces on there, you can do that. And that's a trick that we use in order to help solve these kinds of problems. So we can draw this in the same direction here, just recognizing that the force on here is the force of gravity. Now, we would normally draw it in the y direction, but we can put it in the x direction as well, if we like, as long as we recognize that it is the force of gravity. All right, so from here then, in solving these problems, we start once again with F equals ma, of course, and we need to find out what T1 and T2 are, and that's what we're going to find out. So first, we need to determine the acceleration of the system. And here's another trick that I will show you. In order to do that, so here we've got F equals ma, we're going to write this equation for each one of these masses. And that's going to help us to solve the problem. So first one here, on this mass, the F equals ma equation for this one is just simply T2 equals 3.0 times the acceleration of the system. Now if we look at the second one, it has T1 in this direction, and like we said, it has T2 in this direction. So the sum of the forces on this one is T1 minus T2, and that has to equal 4.0 times the acceleration of the system. All right, then one more, we'll write the equation for the last one, and that's the force of gravity on that object, which is 12.0 times 9.8, minus T1, so again, same sort of thing, we have T1 in the opposite direction of this one, minus T1 has to equal 12.0 times the acceleration of the system. And what we're going to do now is we're just going to add all of these equations together. So we just add them all together and we'll see what happens. When you add them together, what happens is the T2s cancel out because we have a T2 minus a T2, they cancel. And we also have a T1 minus a T1, which also cancels out. So when you add them all together, what you've got is you just simply have 12.0 times 9.8 equals, and this number came from 3 plus 4 plus 12, which is 19 times the acceleration of the system. So this is a really neat trick to just write the equations down, add them together, and then you can find the acceleration of the system, which in this case, is going to be 12 times 9.8 divided by 19, and the acceleration of the system turns out to be 6.2 meters per second squared. So once we have that, then it's a simple matter to find T1 and T2. So we can use this equation right here to find T2, because T2 is just simply 3 times the acceleration of the system, which we just found out. So that's 18.6 newtons. And then we can use one of the other equations. We'll use this one now to find T1. And we put the numbers in here. And so T1 minus T2, which is 18.6, we just calculated that, has to equal 4.0 times the acceleration of the system, or that mass, they're the same. And that will work out to 43.4 newtons. So there's a really clever way of dealing with these kinds of problems, and it's just about getting your diagram right, writing your equations correctly, and adding them together, and then it's just an exercise in algebra from there, really. And now the last thing I wanted to mention was these kinds of problems, they do sometimes get a little bit more complicated when they introduce friction, but it's really not that big of a problem as long as you recognize the direction of friction on each of the objects, and just make sure you include them in your equations of the forces and the accelerations. So as long as your diagrams are correct and you've got your forces in the right direction, your forces of friction, then it doesn't get actually that much more complicated. You just need to account for a couple more forces, that's all.